Good morning. Sorry to miss class this morning, but I don't know if it's allergies or what, but anyway, I decided to just do this through recording. And then if you do have any questions about anything after you watch it, we can talk about it next week when we are reviewing for fluoro and QC. So remember that when we talk about imaging, there's two types of images, analog and digital. Analog referring to a device or system that captures or measures a continuously changing signal. Digital is recorded as multiple numeric values and are divided into an array of small elements that can be processed in many different ways. So, for example, let's see, let's go back to this one. An analog device would be like an old-fashioned watch that has the face on it where it has hands that are continuously moving. And a digital watch would be where you see one specific time of day at a time. So the matrix is the combination of the rows and the columns or an array. The pixel is the smallest element of the digital image. So each pixel within the matrix is going to correspond to a specific location in the image and an area of the patient's tissue. So I have no idea why it turned this slide sideways, but it really doesn't matter. Formatted it different for some reason. The image is digitized both by position and by intensity. So the pixel is going to have a particular location in the image as well as a gray level or a shade of gray that is assigned to it. And in this was the ImageJ software that we used when we were going through this stuff back in the second semester. And so you can see that on the far right of this, even though it's turned sideways, the X and the Y location and that would be the location of the pixel in the image. And then the value was assigned 166 to that particular area where the cursor is in that image. And the typical number of pixels in a matrix can range from about 512 by 512 to 1024 by 1024. Again, the pixel is assigned one discrete value that represents a shade of gray or a brightness level on the monitor. There's many different descriptors that we use to talk about pixels. So pixel size is what the first one we're going to address. Let me turn my phone down here. It's the dimension of the pixel. It's generally measured in microns. So we're talking about very, very small elements in the digital image. You can convert millimeters to microns by multiplying by 1,000. It takes 1,000 microns to make 1 millimeter. When we think about pixel size and how that's related to spatial resolution, remember that the size of the pixel is going to be inversely related to the amount of spatial resolution. So the smaller the pixel size, the higher or the better the spatial resolution. So smaller pixels give you better spatial resolution. Pixel pitch is referring to the distance measured from the center of a pixel to an adjacent pixel. So it is not the same as the pixel size because it's going to depend on the electronics that are actually between the pixels. So that's why it is different. Pixel density is referring to the number of pixels per unit of area. So in the picture on the left, you can see that there's only 5 pixels per millimeter. In the picture on the right, there are 10 pixels per millimeter. So we would say that the pixel density is greater in the image on the right. And when the pixel density is greater, that means the pixel size is smaller, as you can see in this illustration. In a CR system, pixel density is determined by the sampling frequency or the sampling rate. So we can use those terms interchangeably. Sampling frequency, sampling rate is just how often is the computer sampling or acquiring data or information in that image. It's the number of pixels per millimeter that the laser scans with each line. So again, remember, this is only in computed radiography. This is just another picture. You can get an idea of lower sampling frequencies compared to higher and how it changes the size of the pixel. So increasing sampling frequency or sampling rate does a couple of things. It does increase the pixel density. It decreases the pixel pitch or the distance between the sampling points. It decreases the size of the pixel. It increases the spatial resolution. So all those are good things or advantages. These last two would be drawbacks to increasing the sampling frequency. That would mean that it would increase the processing time for the image and also increase the storage requirements. So determining pixel size from sampling frequency, we can figure out what the pixel size is if we know what the sampling frequency is. So we can just invert the sampling frequency. So again, sampling frequency is how many pixels per given unit of measure. So the number of pixels, say, per millimeter. And if we invert that, it would say that, okay, in 1 millimeter, is going to determine how many pixels are in that 1 millimeter. So for example, if we had a sampling frequency of 10 pixels per millimeter, if we invert that, then it says, okay, in 1 millimeter, there's 10 pixels. So how big is each pixel? You just do that division, 1 divided by 10, and that will give you 0.1 millimeter per pixel. If you expressed that in microns, then it would be 0.1 millimeters times 1,000, because there's 1,000 microns in 1 millimeter. So it would equal 100 microns. That would be the size of the pixel. Sorry. That thing keeps doing. So again, if you think about it like in something you can relate to easily, if there's 6 square tiles in a 12-foot section of floor, then how big is each tile? Well, each tile would have to be 2 feet. So just another way to look at it. Field of view, this is when we're still talking about CR, computed radiography. The amount of body part or patient included in the image, which with CR is determined by the size of the IRU. So this is different than what we're talking about when we talk about like when we're talking about a collimated field. It's not the same thing. In CR, the field of view is determined by the size of the IR that you're using. So the larger the field of view, of course, the more area you can image. So if we look at that relationship and see what happens to pixel size if the field of view is decreased. So if we go from using a larger size IR down to a smaller size IR for a fixed matrix size, so we're just changing the size of the IR, not the size of the matrix, then the pixel size has to get smaller. That's a direct relationship. And here's just an illustration of that. So in this picture, the field of view went from, let's say, a 14 by 17 down to a 10 by 12, but the matrix size didn't change. So we're still applying that same matrix size just to a smaller cassette. Then we can see the pixel size has to get smaller in this case, and therefore spatial resolution would get better. And then we can also look at if the field of view stays fixed. So let's say we keep the same size IR, but the matrix size is decreased, then the pixel size is going to have to get bigger. So that's an inverse relationship. So again, let's look at this. So here we're still with the same field of view, the same IR size, but now the matrix size is getting smaller. So if the matrix size is getting smaller, but it's being applied to the same field of view, then the pixel size has got to get bigger. And you can see that visually on this image. Bottom line is just to remember that the size of the pixel is one of the determining factors of spatial resolution when we're talking about CR imaging. So what does this mean for image quality? Again, anytime the pixel size is decreased, spatial resolution is going to increase. And then anytime pixel size is increased, spatial resolution is going to decrease. So think about if you can see pixels in your image. I don't know if it's a real thing or not, but we can refer to that as the image being pixelated, then your spatial resolution is going to be worse. Bit depth is another description that we can use for pixels. It's the number of shades of gray that each pixel can display from totally clear to totally black. It is expressed as 2 to the power of n because the binary system is the machine language of ones and zeros for computers. And so 2 is going to represent the number of possible bit values, meaning 1 and 0. And n is going to represent the number of bits, a single unit of data. So the thing to remember is pixel bit depth does not affect spatial resolution. It only affects contrast resolution, which is what this next slide says. So as bit depth increases, meaning the number of shades of gray that can be displayed increases, then contrast resolution is going to increase. Again, don't confuse this with how we talk about contrast in general. So think about a box of crayons. And so let's say you have a box of 64 crayons compared to 8 crayons. And so if you had areas in the image that were similar but not exactly the same. So in other words, they had just very subtle differences in the amount of exposure to those, in this case, let's say 9 areas. And I don't know why that says red. That should say blue. I'm sorry about that. I used to use red, now I'm using blue. But anyway, in this example, if we have 64 crayons, we might have a whole bunch of different shades of blue where we can assign those very subtle differences in the way in the amount of receptor exposure underneath that particular pixel. We could assign those as several different shades of blue so that we could distinguish them from one another. Whereas if we had a much lower bit depth, say we only have a box of 8 crayons, we're only going to have 1 shade of blue. So we're going to have to assign all 9 of those pixels the same shade of blue. So we're not going to be able to see them as separate and distinct. So you won't, let's see if I have that in here. So the higher your contrast resolution is in your system, then the better, because it means you're going to be able to see more information in that image than if your bit depth is lower. That's the bottom line. Brightness just refers to the appearance of the image on the display monitor. When this second statement says no technical adjustment during image acquisition will change the brightness of the image, it's strictly a display quality. What that means is if we double our mass from one image to another, we're not going to see that change in the brightness of the image because of the automatic rescaling function of the computer. And so it's just saying that with film, if we used one mass on one image and we doubled that mass, we would see the darkness change, what we call density, in that film. And so we don't really see that with digital imaging because the computer is constantly trying to correct exposure mistakes. And we can also change the brightness of the image through the window level function. So window level controls brightness. And in a minute, we're going to see here that window width controls contrast. So contrast resolution, again, is the ability of the digital system to display subtle changes in the shade of gray. And it is very dependent on the amount of scatter. So we know that scatter is very degrading to imaging, whether we're talking about film screen, CR, or digital imaging. We still need to try to keep the amount of scatter that reaches the IR to a minimum. And we can alter the contrast of the way, like post-processing image, post-processing functions that we have are window width is what controls the contrast. Window level is what controls the brightness. So just very similar to your phones. You can adjust the way it displays on your phone. You can adjust the brightness. You can adjust the contrast, just as you can also do on television sets. So, spatial resolution, the ability of the imaging system to demonstrate small details of an object. You might also hear it called the ability of the system to see the structural edges or lines in the image. And so we know that pixel size is a determining factor of spatial resolution. We talked last week, let's see here. We talked last week about the geometric factors that do affect spatial resolution or recorded detail in the image. So those don't change whether we're talking about film screen or CR or digital imaging. Those geometric qualities of the beam still do affect spatial resolution in addition to these things that we're talking about with digital imaging. So the OID, the SID, the focal spot size, those still apply when we're talking about digital imaging. So this is just three different images where you can see as the pixel density is getting greater. So we're going from 20 pixels to 100 pixels on the right. As the pixel density is getting greater, the spatial resolution is also improving because the size of the pixel is getting smaller. There's more pixels per centimeter in the image on the right. Therefore, the pixel size has to decrease, which increases spatial resolution. And then spatial frequency is a measurement of spatial resolution. We talk about it in line pairs per millimeter. A line pair is a black line and an interspace of the same width as the line. So it takes 2 pixels to make up a line pair because you have to have 1 pixel that's black and 1 pixel that is bright or clear, however you want to look at it. So, I already said this. So SID, OID, focal spot still affect spatial resolution. The sampling frequency or sampling rate with CR also affects the spatial resolution. Nyquist frequency is the maximum theoretical resolution that you could see in a system. It's the half of the sampling frequency or rate. So a plate, meaning a CR plate that's scanned using a sampling frequency of 10 pixels per millimeter, would not be able to demonstrate more than 5 line pairs per millimeter based upon the Nyquist frequency. Now, that's in a perfect world, but we know that systems are not perfect. So generally, it would be slightly less than, what your Nyquist frequency actually is. With DR, direct radiography, there is no sampling. There is no scanning of a plate like there is in CR. So the manufacturer is who determines the size of the dale. So that is set during manufacturing. It does not change. We can't change that. The number of dales per millimeter does determine the number of line pairs per millimeter that we can resolve, though. But again, that is something that's set and does not change. Pretty much what you say about a pixel, you can say about a dale. So meaning the smaller the dale size, the better the spatial resolution is. So moving on to dynamic range. So dynamic range is simply talking about the ability of your receptor to respond to radiation, or the ability of your IR to capture radiation by the detector. So you can see that response is plotted on the Y and exposure is plotted on the X. And we would consider it's called a characteristic curve, even though it's not a curve. This is a linear response because it is actually a line. So it takes very little exposure to actually get a response. And that's one of the reasons that digital imaging is as far as over film screen, it was such an improvement in the amount, the little amount that it took to get a response. Now, even though we're going to look at this here and say, okay, well, this response down here in E minus is going to not really be useful information. That is going to be the area of underexposure. But we still get a response. Whereas with film, you wouldn't even get a response until a particular level of exposure. So that's why we say the dynamic range for digital imaging is greater than it was for film screen. EO area refers to the optimal area. So EO is where you want to live. That's the amount of exposure that is adequate and gives you a good quality image without either underexposing or overexposing the patient. So EO stands for optimal. E plus is where you're going to begin to get overexposure to the patient, but the image quality is still going to look really good. Because the computer through automatic rescaling can correct those mistakes. E plus plus is where we're getting to really overexposing the patient, and we may begin to lose some contrast here. The image quality is starting to be affected. And then at E plus 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 is where it has leveled off. If you look, there's a line now, so the receptor can no longer respond, and that's what we call saturation. So that's where image quality is definitely affected, and we've lost data or information that we can't get back. And this slide here is just what I just went over. Now, exposure latitude. So let me go back. Exposure latitude would be EO. That's what exposure latitude is, because it's the range of exposures that produce quality images at an appropriate patient dose. So digital image receptors can generally correct about 50% underexposure to, we say, 100% overexposure relative to the ideal exposure level. Any more than 50% is usually going to give you noise in your image or model in your image. Overexposure of 200% of the ideal is going to result in loss of image contrast. And so we say 100%, but really most systems can correct as much as even upwards of 400% of overexposure. But this second statement is the one that you're going to want to remember, because that's what most books say. Okay, the computer or the system can correct about 50% under to about 100% overexposure. But we proved this in lab, it really can correct much more overexposure than that. But that's not good. Just because it can do it doesn't mean that we need to overexpose our patients. We still need to try to use the correct amount of mass and KVP to get a quality image at a correct exposure dose for the patient. Now, these next 3 slides are sort of dealing with the same thing. We're not going to get into a lot of detail about these, but what you really need to understand is whether you're talking about point spread function or edge spread function or line spread function, it's different ways to measure the ability of the system to form sharp images. So whether we're looking at one particular point, we're looking at an entire edge, or we're looking at a line, they can use these things to derive the modulation transfer function, which is a measure of the imaging system's ability to display the contrast of anatomic objects varying in size, which means it's literally a plot of contrast to spatial frequency. Spatial frequency meaning that's how we measure object size. Another way to think of it is how well is the black and white contrast preserved as the resolution increases. The bottom line is the main thing I want you to remember about modulation transfer function is that it's often regarded as the ideal expression of the image quality provided by a system. So if you are responsible or you're part of a team that is purchasing equipment, then this is something that you would look at. What is the modulation transfer function of the equipment? Just another way to look at this is the top line there, if that's what the object actually looked like, but when you imaged it, it looked like that bottom line, you can see that as spatial frequency increases, meaning like as we would think about the resolution test tool, how as the line pairs per millimeter got greater, it was harder to to distinguish the black from the white, or the black from the very bright or clear. An imaging system with an MTF of 1 or 100% would be perfect. That would be that the contrast was preserved perfectly, and we know that that's not the case. Now it can pretty much have an MTF for very large structures, but most all systems, as you start to increase your spatial frequency, that's gonna drop off. So you can compare different systems. There's actually a good Red Tech Bootcamp video about this, but the main thing that I want you to know about modulation transfer function is this statement here, where it's regarded as the ideal expression of image quality, and it's going to be used when you are purchasing equipment. It's just something that you can look at to help you make a decision about what equipment you want to buy. DQE, detective quantum efficiency, how efficiently the system can convert the X-ray input signal, meaning the exit radiation that makes it through the patient and actually interacts with the IR. How efficiently can it convert that exit radiation into a useful output image? Systems with higher DQE can produce higher quality images at a lower dose. So I don't know if you guys remember when we did this over in the old building, and we did images with the CR and we did images with the DR. We proved that the DQE for DR was higher than the DQE with CR, because we began to get saturation at a lower dose with the DR than we did with the CR. So that proved that our DQE was higher with the DR system. And that's what this statement is saying here. That says more on this later, but we'll talk about that when we get to that part here in a little bit. Noise is anything that interferes with the formation of the image. It contributes no useful diagnostic information. So we can have equipment noise that's just caused by the detector elements or possibly non-uniform responses of the detector elements. There's quantum noise or photon starvation that's described as image noise that's created when we don't use enough mass or we don't produce enough photons to actually create the image appropriately. Scatter noise, we know we try to keep scatter noise to a minimum by trying to restrict the beam size, using grids, using lead blockers when we can, those kinds of things to keep the scatter noise to a minimum. There's also something called ambient noise, which is not on this slide, but ambient noise, excuse me. Sorry, this is wreaking havoc on my voice here. Hold on. So ambient noise is created from general background noise. So with CR, that could be a real problem. If you had CR cassettes just sitting around all weekend, maybe your facility isn't open on the weekend, so those aren't being used. The first thing you'd want to do when you came in on Monday was to erase those cassettes, because they did accumulate background radiation on them. Nothing we can do about that. We don't really have that issue with direct digital imaging, because those detectors are continuously refreshing, and so we don't really have that issue like we did with CR. Okay, signal to noise ratio describes the strength of the radiation compared with the amount of noise. So it's literally just a ratio. Your radiologist is going to decide how much noise they're willing to accept in an image. On this example, you can see that the higher MR dose to the IR creates a better image. The signal is higher to noise. So again, it's like if you're in a crowded restaurant and you're trying to carry on a conversation, it can be difficult to hear if there's a lot of noise happening. So you would either have to increase the signal to noise, you'd either have to talk louder or get rid of the noise. And so in this image, you can see how much better the image is on the left than the image on the right, because the signal to noise ratio is much higher in the first image. So again, signal is good, noise is bad. We also want to consider contrast to noise ratio. Higher contrast resolution means that anatomic tissues that attenuate the beam similarly can be better visualized. So again, higher contrast resolution means we have more shades of gray that we can use, so that anatomic structures that do attenuate the beam similarly, they can be assigned different values so that we can tell the difference in them. Here again is another image. You can see that the image on the left has much better contrast to noise ratio than the image on the right. Image processing and manipulation. In both CR and DR imaging, after the X-ray photons have been converted into electrical signals, those signals are available for processing and manipulation. So that's what was such a big advantage to digital imaging from film screen, is the manipulation capabilities of the image afterwards. So things can happen pre-processing, means this is where the computer algorithms are going to determine the image histogram. So this happens when you're choosing the projection that you're doing, and a particular lookup table is going to be applied to that image. And then there's post-processing, and that's done by the technologist through various user functions. So that's where we could adjust the window width to adjust contrast, or we could adjust the window level to adjust brightness. So the post-processing things are those things that we have those tools on the toolbar that we can make it adjustments to the image. The histogram is the graphic representation of a data set. So it represents the subject contrast in the remnant radiation, meaning the exit radiation, what makes it through the patient. We see peaks and valleys there. That is what the subject contrast is. The x-axis, so it's basically just a plot. So what's plotted on the x-axis are the pixel gray shade values. And then on Y is how many times did we see that particular value in a pixel. So histogram analysis is complex. It provides the basis for automatic rescaling and exposure index determination. So the analysis of the histogram is how the automatic rescaling is done, and determining the actual exposure index, whatever that is, whether it be a exposure index, that should say probably indicator would be a better word there, because indicator is sort of the broad umbrella that a lot of other things fall under, like S value or EXI or EI or EIS, all of those different things that we'll get into here in just a little bit. The shape of the histogram stays fairly constant for each part exposed, meaning a chest histogram is going to look very similar from person to person. And that's why it's important to choose the correct anatomic region on the menu before you expose the patient. So if you're doing a chest x-ray, you need to choose chest from the menu, not hand or something like that, because those are going to look totally different. And that's going to we'll talk about here. So the lookup is going to change the lookup table that's used. So the lookup table is a table of data that converts input gray level values to desired output values for the displayed image. So it's used as a cross reference to transform the raw information. So what it's doing is it's taking that information, and if your data set doesn't match that lookup table, then it's going to change those brightness levels so that and that's called automatic rescaling, so that it displays the same. So in other words, it's going to try to fix the brightness so that the images look the same whether you use the right amount of exposure or not. This is just showing you how that's done. I don't know if you guys remember when we did ImageJ software, but the contrast of the image is increased or decreased by changing the slope of that graph. That's how you change contrast. The brightness or the density was changed by either moving the line up or down the y-axis. So contrast was changed by changing the slope. the brightness was changed, the slope didn't change, but the just sliding that up or down the y-axis is what changed overall brightness, or I don't like to use the word density anymore because that's an old term. So the window width, again, I said, is what allows you to adjust your contrast. So you can see here, I like this example. You can see that a narrower window width gives you higher contrast. With a wider window width, you have lower contrast. There's just more shades of gray there that can be displayed. Brightness, you do that with adjusting the window level. So it's setting the midpoint of the range or the brightness that's visible in the image. It changes the brightness throughout the entire image, the same amount. So whereas contrast is changing them where there's differences, because that's what contrast is, brightness is changed the same amount throughout. It's just the level of the midpoint of the brightness range that are available in the image is changed. So you can see that in this picture. The brightness midpoint in the picture on the top is 4. In the picture on the bottom, the brightness midpoint now is 7. So the brightness of the entire image is being changed the same. Like each pixel is being changed the same amount. So histogram analysis errors can occur. And when that happens, that means the exposure indicator might be inaccurate. It can happen when the incorrect exposure factors are used or the wrong lookup table is selected. If your centering is poor, if you have poor collimation, poor beam alignment, if you have a low intensity radiation response, meaning you didn't use enough mass to get a good response from the image receptor, or if you have poor scatter controls, or you have a whole lot of scatter that's reaching your IR, whether that's because you didn't collimate, or you should have used a grid, or you didn't use your lead blocker on a lateral lumbar or sacrum coccyx, whatever it may be that you're doing there, or maybe your KVP was too high. All of those things can cause issues there. So automatic rescaling, again, I mentioned just a minute ago, it compares the obtained histogram with the lookup table, and it reassigns pixel values to bring it in line with the ideal of the lookup table. So there's a way that the computer expects it to look, and if it doesn't look that way, then it's going to make these adjustments to the pixel values so that it does look the way it expects it to look. So if you're overexposed, it's going to rescale it lighter. If you're underexposed, it's going to rescale it darker. So we get a uniform display brightness. We can get a uniform display brightness over a wide exposure range. Now, sometimes automatic rescaling is going to fail. When you have overexposed the patient to the point of saturation, or you have underexposed the patient and you have photon starvation or quantum model, it can't fix those things. So everything has limits, but it does have the ability to fix a lot of exposure mistakes. But we don't want to depend on that. We want to try to use the amount of exposure that's appropriate for that particular patient, size, condition, whatever. Subtraction is a function that can be used to remove superimposed structures so that the anatomic area of interest is more visible. So what happens is the computer is going to subtract out particular brightness values to create that image without those superimposed structures. So like, for example, in this image, you notice that the bones or the bony thorax has been subtracted out to where all we see like are the soft tissues, the lungs. I thought I had another picture. There's another picture, I believe, in your book that has the soft tissue structures subtracted out, and all you see is the bony thorax. So it's just a different function that is available generally post-processing. Or like when you're doing fluoro procedures, things like declots, you can do subtracted images from those so that you're subtracting out all the bones and stuff, and all they see are the vessels left. So another post-processing function is edge enhancement. It increases contrast along the edge in the image. And so in the bottom part of this image, you can see that the the edge enhancement has been applied, and so you get this higher contrast right along the edges of the image. This is known as high pass filtering, and unfortunately you just have to memorize that. If it's overused, it can cause what looks like a halo effect. Let's see if I have a picture. I didn't have I tried to narrow this down some because I couldn't possibly reteach everything that we learned in like 6 weeks in 2 hours. But anyway, it can create a halo effect around in parts of the image. So you don't ever want to overuse these things. Sometimes less is more. So inversion is a technique that reverses the grayscale from the original image. It can also be known as black and white reversal. So everything that was very bright is now dark, and everything that was dark is now bright. It just inverts the grayscale of the image. And this is nice to use sometimes if you're trying to tell if you've got that. You may see text do it if it's like super close on the rib margin and they're trying to tell if they got the rib, or sometimes it's easier to see a feeding tube placement when you invert the image. But anyway, you don't want to leave it that way. You want to anytime, well, I'll go ahead and say this, any post-processing that you do, you generally want to undo before you send it to the radiologist. So it's fine to mess around with it if you're trying to see something, but generally you want to give them the original information so that it does not limit or narrow what they have the ability to do when they get it from PACS. Smoothing is another software function. It sort of suppresses image noise. It's known as low pass filtering. Reduces the graininess and contrast, but the edge is still degraded. So I don't really love smooth. I mean, if your image has noise in it, the best thing that you can do is repeat it. So I don't like using smoothing because if you remember, if you can see noise in your image on your monitor, the radiologist is going to be able to see it a lot more on there. So if you're picking up noise on the image, the best thing to do is just go ahead and repeat it. Equalization is where areas that are underexposed can be made darker and overexposed areas can be made lighter. So things like oblique C-spines, sometimes it can be used to expand that histogram and fill that entire grayscale in localized areas. So in this example, you can see that now you're better able to see from C1 down to C7 T1 when the equalization function or tool is used. Now getting into the specifics of how these IRs work. So PSP, cassette-based PSP systems differ from conventional radiography in that the cassette is simply a light-proof container. So with film screen, we did have these cassettes, but they housed the film. So if you opened them in white light, the film was ruined. You have to replace it. You had to open those in the dark or in a dark room. Dark room itself with the red safety lights. The plate in PSPs takes the place of that film, and that is where the image is stored until it is put in the reader. The different layers of that imaging plate, it has a phosphor layer, which is considered the active layer. This is where the electrons are trapped during exposure. So this is where your latent image is stored until it is put into the reader and then scanned by the laser. You can have different, so again, we have the active layer here. This is the phosphor layer. So we can have different types of phosphors in the active layer. We have what's called turbid, which means they're just random distributions of the crystals. Generally, these come from the barium fluorohalide family. Or you can have needle or columnar type of phosphors. And so this is generally what more of the CR cassettes have gone to. They have less light divergence than the turbid ones. They were generally made of cesium iodide. So we're going to get to this again, something similar when we get to the TFT technology as well. But so you would make your exposure to your plate, then you would put it in a reader, and the reader would remove that plate and scan it with a laser. There were two types of PSP readers. You have point scan and line scan. Point scan means it literally reads it a point at a time. Line scan means it read it a line at a time. That was generally done through a CCD. There's two scan directions that we can think about. The fast scan was movement of the laser across the plate. So the plate itself was stationary and the laser just moved across the plate. Slow scan was the movement of the plate through the reader. So instead of the laser moving, the plate itself moved. And there's also two other terms for that. I don't know why, but it's called translation or subscan. It can also be referred to as slow scan. I'm not going to take a whole lot of time on this. I'm hoping that the registry is moving more away from some of this CR technology because it is sort of going by the wayside. But it was the laser would move across the imaging plate, sort of like holding a flashlight. So things like the optics, you wanted to keep the same, the beam size, the shape, and the speed, so that every part of the plate was looked at the same way, so that you didn't get different outputs or different spatial resolutions, things like that. You wanted that to be consistent. The reader generally scanned the plate with a raster pattern or zigzag. Gave energy to those trapped electrons that were stored in the phosphors there in the CR plate. And then the scanning process would produce lines of light intensity information that was detected by the photodetector. And then that photodetector would amplify the light and send it to the ADC, or the analog to digital converter. So that was CR. Now flat panel detectors, which is generally what you're going to see being used out there. TFTs, thin film transistors, is pretty common technology. The choice of the absorption material determined whether that detector itself was considered direct conversion or indirect conversion. So it's easy to get confused when we talk about direct radiology. We're just talking about the fact that there is no reader. Everything it's processed within that detector itself. But with flat panel detectors, we can divide that down even further, and we can say, okay, depending on what kind of absorption material is in it, is going to determine whether there is a direct conversion directly from electrons into our signal, or indirect, where there's a light step involved. So indirect, the X-ray photons are absorbed by the material and immediately converted into signal. So I might have said electrons a minute ago. I meant to say photons. The photons interact with this, in this case, it's generally amorphous selenium. That's the photoconductor. And it converts them directly into electrons. So you go from photons interacting with this photoconductor into signal. There is no light step, no light give off in a direct conversion type of TFT. In an indirect type, then the photons interact with the phosphor layer that's known as the scintillation layer. And we know that scintillation means that light is going to be given off. So that scintillation layer can either be structured or unstructured. So again, we go back to turbid or columnar or needle type of phosphors. That's talking about the scintillation layer. So the turbid type, generally were gadolinium oxysulfide. They're very rugged. The cesium iodide needle type worked more as light directing tubes. So there was less light spread, which means they would have higher spatial resolution. There was higher DQE with these. So generally the detectors that I have used and like that we have in the lab now and that we had in our old lab were cesium iodide type of detectors, or that would be considered in indirect conversion because there's a light step. So let me go back here. Whoop. So you have the photons interacting with the scintillation layer where light is given off, and then the light is converted to electrons or signal. And then that is digitized, and it depends on again which type of detector you're using. So this is just a breakdown of the two different types of conversion. So you can see in the indirect you have the photons to interact with the scintillator, which gives off light and then is converted to electrons, and they're collected in the TFTs, and then that analog signal is converted to a digital value. In the direct conversion system, you have the photons interacting directly with the amorphous selenium, and I don't have it on the left. It's amorphous silicon. Oh yeah, I do. There it is in big letters. Amorphous silicon is the photodiode. The photoconductor on the right is amorphous selenium, and so those photons are converted directly into electrons, and then the process is the same. They're still collected by the TFT. That analog signal is then converted to a digital value through some sort of analog to digital converter system. The TFT array is divided into square detector elements. So instead of pixels, we have dales. Each has a capacitor to store electrical charges and a switching transistor for readout. So with the TFT, it's read line by line. The size of the dale is set during manufacturing, so it can't be changed. But just like with smaller pixels, smaller dales result in improved spatial resolution. But fill factor is something to consider. So let's look at fill factor here. Fill factor is the ratio of the sensitive area to the entire detector area. So the area that's actually going to be interacting with the photons, that's what you're talking about, fill factor. And it does affect both spatial resolution and signal to noise ratio. Okay, I thought I had another picture in there. So so we've been talking about TFTs. Now we're going to talk about the CCD, charged coupled device. So this is where your X-ray photons interact again with the scintillation material in the CCD chip. So this would be considered an indirect conversion system because there is a step of light that is given off. So that light is then converted to electrical charge, and then that is transmitted by lenses or fiber optics to the CCD. So the TFT is read line by line. The CCD is read through the bucket brigade. So again, think about an array of buckets, or pixels or dales is probably a better term there, collecting rainwater. Each bucket is exposed for the same amount of time to the rain, filling up with varying amounts of water, and then it's read one bucket at a time by pouring water into the adjacent empty column. I thought I had a picture of that too, but anyway, you can look back at the older PowerPoints that I have available to you in Blackboard if you want more information on that. CCD advantages over TFT. The CCDs are simple and modular, which makes them easier to repair, replace, and upgrade. So what that means is if you have a problem with your CCD type detector, there's a good chance that maybe it can be fixed. Whereas with TFTs, if they go bad, you have to replace the whole thing generally. So we actually had that happen back a couple years ago in the lab. I don't know if I can't remember if y'all knew about that or not. And then we have the CMOS, or complementary metal oxide semiconductor type of detector, which uses P-type positive and N-type negative transistors that form a gate that can be controlled electrically. So it basically works the same as a CCD until the read off of the chip. In the CMOS, each individual dale has its own transistor, amplifier, noise correction circuit, digitization circuit. So it's not like the bucket brigade. Like every single dale has all of that built into it. So it actually can have a little bit more noise in it than the other systems, but The main thing that I want you to remember is TFTs are read line by line. CCDs are read through the bucket brigade, and CMOS, every single DAL has all of that technology built into it, and each DAL is read. So that's the difference in those. Now, which of these has the highest DQE? So this, again, detective quantum efficiency. Amorphous selenium detectors have the highest DQE because they do not have the light conversion step. So there's no light spread, there's no light to blur the recorded signal output, the less doses required for the others, higher quality images are produced. However, they're working on that. Newer CMOS capture systems can be equal to direct image acquisition because the crystal light tubes, which also prevent light spread. So this is constantly being tried to be improved upon. Now, these next two things are just a couple of things that are newer technology. I'm not giving you a lot of information on them because there's not a whole lot of information out there about how they work. A lot of this technology is very proprietary. So they keep a lot of the way these things work sort of under wraps. But AEC technology, AEC assistance technology is similar to the way the AEC works. But the nice thing about this is that it is actually built into the detector itself. So you can use these detectors with portables or tabletop stuff that you can't do when you're talking about traditional AEC. So I'm not going to pretend to understand exactly how this works because there's really not a lot of information out there about how it does work. But it enables the operator to specify a particular pixel value, and then it will automatically send a signal to the generator to stop the exposure when that value is reached. So similar to how AEC works in that when a certain amount of exposure or signal is collected in the photocell, it sends the signal to the generator to cut the exposure off. It works similarly to that, but I don't know exactly how. It has to do with the pixel values themselves, and that's why you can use it on portables or tabletop because it's built into the detector itself. And then dynamic digital radiography. Again, I haven't actually seen any of our sites have this, but it's where you have a series of individual digital images taken with regular x-ray equipment, but they're acquired at really high speeds and low doses. And then they can loop these images together so that it looks like almost like a movie. So you can see dynamic motion of these anatomical structures. It's not fluoroscopy, so it's the dose is much better than fluoroscopy. So things like sniff tests, where they're looking at how the patient's diaphragm works, if it's functioning properly. This can be done using DDR instead of fluoro, and it saves the patient dose. It's marketed as X-ray that moves. That's their big pitch. And so if you click on this link here, it'll take you to just some general information about one of the Shimadzu has this technology in some of their equipment, but it can be very useful for, like I said, in pulmonology for things like sniff tests, also for things like lateral C-spines when they're maybe looking for whiplash and they want to do flexion and extension, so they can have the patient flexing and extending and do these images and then loop them together, and it'll look like a movie or a video. And I think that is it. That's enough. If there's anything that I mentioned that is still unclear to you or you have questions about, you can either just email me or we can talk about it next week during class. And again, I did put the entire PowerPoints in Blackboard from spring semester of all this stuff. So this was just trying to hit the high spots. But if you look back through those also may be helpful because they have just a little bit more information in them. But anyway, I guess I will just see y'all next week. And then we have spring break. Thank goodness. But anyway, y'all have a good rest of the week.